Hello, I'm Robin Cole, and welcome to the Satellite Image Deep Learning Podcast. In this episode, I caught up with Nils Lehmann to learn about uncertainty quantification for neural networks. The conversation begins with a discussion on Bayesian neural networks and their ability to quantify the uncertainty of their predictions. Unlike regular deterministic neural networks, Bayesian neural networks offer a more principled method for providing predictions with a measure of confidence. Nils then introduces the Lightning UQ Box project on GitHub, a tool that enables rapid experimentation with a variety of uncertainty quantification techniques for neural networks. Model interpretability is a crucial topic, essential for providing transparency to end users of machine learning models. I hope you enjoy this episode. Hi, Nils. Welcome to the podcast.
Hi, Robin. Thanks for having me.
It's my pleasure. Let's begin with where you work and what you do.
I'm currently a second-year PhD student at the Technical University of Munich, and I'm supervised by Professor Xiaoxiang and Jonathan Bamber. And I'm currently working on sea-level rise related machine learning problems, I guess. And I'm broadly interested in Bayesian deep learning, generative modeling, and how these methods can be applied to Earth observation or other data sources. And besides, I'm also quite passionate about open source contribution, which I guess might be a bit of a topic in this session.
Naturally. So I think most people will be familiar with generative AI at this point. Do you mind giving us a quick idea of what Bayesian methods are?
Yeah, sure. So, by default, sort of the most of the neural network architecture and so on that we use I just stay with supervised learning, deterministic in the sense that the output you give it and the output that results through a forward pass will be the same every time. And then there are some methods that also keep a deterministic forward pass, but maybe output some other parameters. But by default, neural networks are not able to quantify uncertainty. And this is ultimately something we would like, because we want to have some sense of uncertainty in the predictions that our model is giving us. And one way to enhance neural networks to do this stuff is Bayesian methods. And the rough idea is that instead of having just point-wise network weights, you try to model each network weight by a distribution, most commonly by a normal distribution. And then there's several approximations you need to take, because in practice, like doing that fully would be computationally infeasible. But as a result, you can then sample these weights and practically do multiple forward passes, and you get a slightly different result every time. And that gives you a notion of uncertainty that you can then compute. And so, there exists a range of methods, but ultimately, sort of that's their goal.
Yeah, I'm quite interested to understand the difference with supervised methods, where obviously if you have a binary classification, it would say 80% probability class A or 20 B. That already sounds like a kind of uncertainty. How do the Bayesian outputs differ?
So for classification problems, you have these most normally by binary or other just by using the softmax, have a notion of probability. There's several papers that these so-called pseudo probabilities are quite miscalibrated, meaning that they sort of don't align well with the empirical underlying distribution. And so that's why in the classification setting, there's still people that try to then go to different approaches to try to fix this miscalibration. There's a whole range of methods that people have come up with. And in the Bayesian sense, you would then also try to get a distribution over different softmax outputs or so, in the sense. So that's in the classification case, but sort of in the regression case, for example, if you just stay with a single target regression output, then you just get one output value, and you don't have this softmax where you can interpret some sort of probability. So there actually this becomes maybe you really need to go to these sorts of methods to even get a notion of uncertainty.
Right. So going from kind of pseudo uncertainty or no uncertainty to a well-defined uncertainty distribution, essentially.
And so well calibrated uncertainties. Although I mean this is also sort of a topic, because when you start looking into uncertainty, there's unfortunately no ground truth uncertainty. So for any given example, you can't really say, oh, well, the output should be this and the right uncertainty is this, because that's just impossible to do. And similarly, you kind of need to work also with other metrics to try to get a sense of how well calibrated these are. And most of the calibration methods, for example, they are computed across a whole data set. So even within that, you might get a notion of the performance of a model for a data set. But then, let's say during production, or when you try and do a predict step for any particular sample that you pass through, you again don't really have that notion. So from a metric standpoint, it gets a bit more involved. But I think it's quite necessary, especially for Earth observation tasks.
100% agree. This is probably a good time to start talking about what you've been working on specifically then.
Sure. Yeah, would love to.
Okay, so your project on GitHub, Lightning UQ Box. Do you mind telling us what that is?
Sure. Yeah. So I first began looking into uncertainty methods during my master thesis, and I sort of found it difficult to find sort of a range of different implementation, because from the machine learning literature, by now there exists tons of methods. And my supervisor at the time, Eric Nellisnik, so one thing he said that also recommendation for a PhD was, a good thing is how quickly you're able to iterate through experiments, in the sense that if you think, well, maybe this method should be interesting because of this property, it might work well, then it shouldn't take you long to just try that idea, because otherwise you're just stuck in like long cycles. So when I then began my PhD here, I thought it would be good to have some sort of common framework where you implement a variety of methods from sort of different theoretical underpinnings, with the exact idea that, hey, for your data set, sort of shouldn't really take that long for you to just try a Bayesian methods. And so, that's sort of a motivation to make this a bit easier.
Okay. So I can get a really tangible feeling for how this works in practice. Is it take typical models and then add some extra capability to them? Is it a totally new kind of model?
So there's some approaches, they just work on deterministic works, so you don't really need to make any changes to the architecture. But for example, in Bayesian methods, where you then try to model your weights, not just pointwise, but as a distribution, you obviously have to make some changes to the architecture. And with all of these methods that we've implemented so far, we've tried to sort of keep it that you still have all the flexibility you want with your network. So all these methods sort of just take a Pytorch architecture, and then we'll make the necessary changes under the hood, for example, to convert it to a Bayesian neural network or so. So we sort of try to keep the constraints on the user as small as possible, but at the same time hope to illustrate sort of how these methods work, so people get an understanding of them, but aren't held back by having to implement a new Bayesian neural network every single time they want to use one.
Mm-hmm. Okay. Sounds good. And if somebody wants to use it, what do they need to know? I see you got Lightning in the name, so I'm assuming it integrates with the Pytorch Lightning training framework.
Yeah, exactly. So fortunately, we're in sort of an area where lots of research code is actually published. And so we've been looking at lots of these research implementations with the accompanying papers, but often those are written specifically for that paper or project with lots of additional code for like visualizations and whatnot. And Lightning is very nice in the sense that it gives you a certain structure in which to implement methods. And so I think from one side, it makes it clear to understand, well, what's actually happening in like one training iteration when you train this or that method. And so because with Lightning, then I would exactly know where to look for this sort of information, while in like a big custom Pytorch implementation, I might have go through different files and see, oh, where is this happening? And the other is that it provides you so much useful properties for scaling, like multi-GPU training and so on, or logging. And these are all things that for researchers, you shouldn't need to spend like additional code or time to just try these things. And so since Lightning gives you so much of this flexibility, we want to sort of fit in that framework.
Fantastic.
So that's sort of the motivation for Lightning.
Right. So you need to be a little bit familiar with Pytorch Lightning, but other than that, it will look standard. You've got lots of different techniques in there. You have a few tutorials as well. Do you mind just telling us what they cover?
Sure, yeah. So the tutorials cover, I mean, in a sense, a bit of, we hope to illustrate these methods, but they also provide a bit of a sanity check to see how they work on like, these simple toy problems. And so I'm not sure if it's useful to like share the screen or something for.
Yeah, why don't you do that?
Okay. So this is just the docs page where we try to give an overview over the different methods that we've implemented so far. But we're also looking to add new methods or have suggestions. So very much looking for feedback. And then on the tutorial side, in a sense, for a lot of these concepts for uncertainty quantification, like 1D regression examples are quite nice, just because you can clearly illustrate things. And so they sort of all follow the same setup, where maybe because we talked about some Bayesian methods before, we can pick this one. So we first tried to give sort of an intuition about like a rundown explanation of what this method does, with some rough notation, but we tried to link to the papers to sort of give a more rigorous derivation for the people that are interested. And then don't need the import statements. And then basically we've just set up a small toy data set that you can also find these types of data sets often in those machine learning papers where they introduce such methods. And then maybe to be also a bit more concretely sort of what a person or user would have to do. So previously I said sort of you can bring your own model. Here we just use a simple multi-layer perceptron with input, some hidden layers and some outputs, and then each UQ method is implemented as a Lightning module. So for the people familiar with or unfamiliar with Lightning, or familiar, you basically, for a Lightning training, you need a Lightning module. That's sort of your model, and it describes what the model should do during training, validation, and testing. And then you need a Lightning data module, which sort of handles the data splitting and the data loading. And those two combined with a so-called Lightning trainer can then execute the training. So for in this case, the Bayesian neural networks would take in the network that we defined above. You can also use sort of any optimizer you want that you see fit or you can try out. And then this parameter is for these Bayesian methods. There was a recent paper last year where that showed that even you can just make some layers in your neural network stochastic or make them Bayesians and keep the other ones deterministic, and you can still get very good performance. And so this sort of reduces a bit the computational load that these methods can have. So that's something these can do. And then you define how many samples you want to draw during training and testing to train your methods. And then you pass in the trainer, and exactly then you can execute the training and see the prediction. Mm-hmm. So you could probably certainly tune these models like in the way you want, but we sort of just illustrate to sort of keep a base case. And so now you can see that you actually have some uncertainty bands that come with your model. Mm-hmm. Exactly, yeah. And then that's sort of the format of all these different tutorials.
Mm-hmm. And I believe you have a remote sensing specific tutorial as well.
So ultimately we're of course motivated by Earth observation data, but usually in that case, just handling the data is a bit more involved. But we're hoping to add more tutorials. So this is one, this might also be nice because recently there's been a lot of research in a field called conformal prediction. And conformal prediction is also a uncertainty quantification method that works on just pre-trained neural networks. So you don't need to change your architecture or anything. And so the primary aim of that is looking at coverage, in the sense that the prediction sets or intervals that your model outputs should contain the true value with a specified value of alpha. There's this tutorial, I think this linked somewhere, but there's some great tutorials for these conformal methods for people that are interested. But for this tutorial, we chose the V645, I'm not sure actually what the pronunciation is, which a classification data set from that can be loaded with Torchgeo. So for conformal prediction, you always need a separate calibration data set. So we've just implemented that. So there's a total of 45 different classes. And in this case, we also use, we thought we could just illustrate again how you can bring your own model. So in this case, we use a pre-trained Sentinel-2 model from this accompanying paper, from the SSL for EO paper, and train it with the Torchgeo trainer class, or more specifically, just actually fine-tune it. So we've done that, so you don't have to do this fine-tuning. But sort of the interesting metric to look at with conformal prediction is this coverage parameter. And so here we see we get 0.79 coverage. And now, so practically speaking, from the implementation standpoint, it's again that we have this method, you just pass in your model, you specify the alpha value. A commonly one is 0.1, which means that you have a desired coverage rate of 90%. So over your data set, over all the examples that you have, in 90% of the cases, the true label should be contained in the prediction set that your model is giving. And currently we just have a deterministic network that it gives you just the highest softmax score as a class output. And this RAPS conformal method actually gives you a prediction set. So it gives you a range of possible values. And the idea is that you want to achieve high coverage, but under sort of a minimized prediction set, because you could always just output all classes, you would have perfect coverage every time, but that's of course not very useful. So it tries to minimize the set size. we can use that, and then we can see here that the coverage has indeed increased substantially from 0.79 to now, higher the coverage value that we wanted at least. And you can also see that the set size has, of course, increased a bit, but this sort of gives you an informed way of how you should construct these set sizes. Mm-hmm. And we've also made a example. So this is the input image. The true label is harbor. So if you actually look at the logit or predictions, then the highest value that the model would actually predict is bridge, which you might say might also be reasonable because these things might look like bridges. But the prediction set that we get out with the RAPS method contains bridge, harbor, and ship. So we can see that by applying RAPS, the true class is actually then contained in the prediction set. So it's sort of an illustration of these of a simple classification class, and we're currently working on some segmentation examples, since a lot of tasks in EO are segmentation or pixel-wise regression cases.
Thank you for that introduction and that overview of that particular tutorial there. Why don't we just go to the GitHub repository page, and we can leave people with that view there. Yeah. And in the meantime, I'm also interested, obviously, to know what your ambitions are for this project, what you would like people to do, how you'd like them to contribute potentially.
Sure. So, to be fully honest or transparent, as in the recent, I think, very recently I also discovered there's other groups that are starting to work on this sort of software packages. So there's one called Torch Uncertainty, and then also one from Posteriors from the Neural company. A company called Neural. So it's definitely, there's some movement in this space, so to say, which is overall, I think that's really cool. But obviously we've also done quite a bit of work, and the overall aim is sort of that we want to, at this stage, provide sort of a starting basis for people to see how one could implement all of these methods. And of course, we want people to use these methods and see how they work for their problems and how the implementations could be improved. Because, if you just work with a couple of people to implement these methods, you might not consider all the different ways that people might want to use it. So, really looking for people to provide feedback and try these things out, because, the spirit of this is very much open source. So that all people can make contributions or recommendations or whatever. This is just this sort of also explained on the GitHub page or laid out in the GitHub page a bit. This again just has the overview of the methods, and the package is now on PyPy, so it can be just installed with pip. Ultimately, I think there's lots of different other methods that are interesting, especially from the generative modeling side. Diffusion models are sort of a very hot topic for all different things, but oftentimes I think they're also just tailored for natural RGB images. So I think there's some customizations that are necessary when working with EO data. And I think those are also things that could be made more simple. There's tons of things out there, and we just if people want to try it out and provide feedback.
There you have it. That's the place to go. And if people want to follow your updates, which is the best platform?
Currently we just have the GitHub page that we make, that we follow or make all the updates to. We're going to do a release kind of soon, but currently we don't have any other platforms set up for communication, etc.
And you personally, you're active on LinkedIn, Twitter, the usual places, and presumably.
Twitter or email, you can definitely reach me. I think this is also on my GitHub profile. So that's probably the easiest way to reach out, or also some of these other people that have been involved. So namely, mainly one collaborator from DLR, the German Space Agency, Nina Gottschling. So we sort of started this a while ago, and we're hoping to continue this work.
Fantastic. Well, thanks so much for the overview. It's a really interesting and important topic, I think, model interpretability.
Thanks.
Best of luck with the development and the PhD, and I look forward to hearing updates in the future.
Awesome. Yeah. Thanks very much for having me.
Cool. See ya.
Bye-bye.